Hello and welcome to another Ostrich video and the second episode of our instrument series. And today we are going to talk about the magnetic compass. The magnetic compass is an instrument we find probably in every aircraft, from a very simple ultralight to the most sophisticated jet fighter. Usually we are using the magnetic compass as a backup or as a reference for our gyro compass. And the reason for this is very simple. The magnetic compass, as its name suggests, is using the Earth's magnetic field to show the direction. And this is not going to fail suddenly on us as other aircraft systems might be. But on the other hand, the magnetic compass is far from perfect. It has several systems errors due to its construction and also due to the imperfections of Earth's magnetic field. And it's also not so straightforward to use as you might think. And so in this video, I want to take a look on all these little caveats. The compass construction is relatively simple, as you can see in this picture. We have two magnetic needles that are connected to the compass rose, and the rose can rotate freely around its center point. And as the needles always point to the north, the compass rose also always points to the north. Fairly simple. And the whole mechanism is housed in an alcohol or oil-filled case with a window and the line so that we can read off the correct heading. And we use alcohol or oil to firstly dampen and stabilize the movement of the compass rose, and second to avoid that the whole mechanism gets frozen due to very low outside air temperatures. But the first strange thing of the magnetic compass is that it appears to turn the wrong way around. As you see in this example, we are flying directly to the north and we are going to turn towards the east. So that's a right-hand turn, and we also would expect the compass to turn right as well. But let's see. And the compass turns left. That seems to be a bit confusing, correct? But it becomes much more obvious if we look to the whole situation from above. And again, we assume we are flying to the north. So the needles point to the north as well, as you can see here. But we are sitting in our aircraft and looking from the back onto the compass. So we see the south end of the compass rose, and that we are still able to read off the correct heading. The indication on the compass rose is mirrored, and therefore also the movement of the rose is mirrored, and the compass appears to turn in the wrong way round. The second error I want to talk about is the so-called acceleration error. And to understand this, we have to talk a bit about the imperfections of Earth's magnetic field and how the compass compensates for this. Here you see a simplified picture of Earth's magnetic field. And you see that the field lines are only at the equator parallel to the ground, and they tilt towards the poles, and at the poles they are perpendicular to the ground. This divides the magnetic force acting on our compass needle in a horizontal component, pulling the needle towards the north, and a vertical component, pulling the north end of the needle down to the ground, or at least that's the way in the northern hemisphere. The horizontal component is what we need for navigation, and the vertical component is reducing the accuracy of our compass needle as it gets tilted down. At the equator, everything is fine. We have only the horizontal component, and the vertical component is negligible. And if we are very close to the North Pole, we have nearly no horizontal component and a mostly vertical component. So our compass needle gets pulled to the ground and it's basically useless for navigation. In Europe, Asia or in North America, we have the horizontal component and the slight vertical component that reduces the accuracy of our compass. And as most planes fly in this region, the compass manufacturers compensate for that. And to do this, we attach a small weight on the south end of the compass needle. Now, the vertical component of the magnetic force is pulling the north end of the compass needle down. And the south end of the needle gets pulled down by the gravitational force of the additional weight. And as the weight is chosen so that the forces are roundabout equal, the compass needle stays level and therefore accurate. It's the same like a balance with two equal weights on either side. So far so good, but the additional weight introduces the so-called acceleration error into our compass. If we change the speed of our aircraft, so we accelerate or decelerate, we have the acceleration error. And this one is the biggest if we are flying directly to the east or directly to the west. And this error don't come into play when we're flying directly to the north or directly to the south. So to understand how this works, let's assume we're flying directly to the east. So that's our needle here, pointing towards the north, and here we have the east indication. So now the south end of the needle has an additional weight, and therefore it has a higher mass and therefore a higher inertia. That means that the south end of the needle now changes its velocity slower than the north end. So if we accelerate, the south end stays behind and tilts the needle like you can see in this picture. And the result of this is that we get an indication that is too far north. If we decelerate, the opposite happens. So the needle tilts like this, giving us an indication too far south. The next one I want to talk about is the so-called turn error. As you see here, the pivot point of our compass rose is higher than the center of gravity, what would be roundabout here. And this stabilizes the compass in most conditions, but it also introduces the so-called turn error. If we turn our aircraft is of course not longer level. Also, the compass then subsequently is not longer level and the compass rose tilts. And in this situation, the vertical component of the magnetic force from the Earth's magnetic field comes stronger into play. In short, if you are in the northern hemisphere, the north end of your compass needle gets pulled towards the dropped wing. So let's assume we are flying eastbound and we want to turn to the north. So that's left-hand turn and it means we are dropping the left wing. So the North Pole now gets pulled to the left by the additional vertical component, and the horizontal component, what we want for navigation, is pulling our compass rose also to the left as we are flying a left-hand turn. And this means our compass rose turns faster than it should be. And therefore we have to stop our turn before we reach our north indication, because otherwise we will overshoot our turn. Now let's assume we are flying to the west and want to turn north again. That means now we are dropping the right wing, and that means that our north end of the needle gets pulled towards the right. The compass rose, on the other hand, gets turned to the left. And that means both forces combined slow our compass rose down. So again, as we are coming from the other side now, we have to stop our turn before we reach the north to avoid overshooting our heading. So to summarize, if you are turning to a northern heading, that means something between 271 and 98 degrees, you have to stop your turn before the indication reaches your desired heading. And if you're turning to a southern heading, that means something between 91 and 296 degrees, you have to stop the turn after your desired heading was indicated. And if you are turning directly to the east or directly to the south, this error doesn't apply. And the errors we talked so far doesn't apply in an unaccelerated and level flight. And this is also the reason why you only cross-check your gyro compass with the magnetic one in an unaccelerated level flight. Now the next two errors I want to talk about are permanent errors, and we usually already account for them during our flight planning. The first one is called deviation. Now our aircraft is usually built from metal, which influences the magnetic field, and it's also full of electronics. And as physics taught us, if a current flows through a conductor, it introduces a magnetic field around it. And this magnetic field, of course, messes with our magnetic compass. The aircraft manufacturer accounts for this, so usually he places the magnetic compass far away from all these error sources. So that's the reason why you will find the magnetic compass never in the instrument panel. It's usually above the instrument panel or below the ceiling. And to further correct for this error, the manufacturer places small magnets inside the compass depending on the electronics you have in your aircraft. So if you change avionics, you have to do these tests and calculations again. But all these corrections can be never perfect. The aircraft manufacturers are doing a good job to reduce the error, but we still have to correct for it manually. And to know how to do this, we find the deviation table next to our compass. And this telling us the remaining error and how we have to correct for it. So if we take our Comanche, for example, we have the deviation table here, and this states if we want to flying directly to the east, so 90 degrees, we actually have to correct 2 degrees and fly on a 92-degree heading. And the last permanent error I want to talk about is called variation. So when we navigate, we use true headings, and true headings refer to the geographic North Pole. Our magnetic compass, on the other hand, is always referring to the magnetic North Pole. So our magnetic heading is always a little bit off. And again, we have to correct for this during our flight planning. And to correct for this or know how much we have to correct, we have to look at our flight maps. And so as you can see here, we have these dotted lines called isogones, and they marked with a number in degree and an E for east or in W for west. And now every point on this line has the same variation. And in our example here, it's 2 degrees east. And when it's east, you have to subtract as a number of degrees from your heading, and if it's west, you have to add. So that was it for this video about the magnetic compass. I hope you found it interesting, and also if you have questions, write it in the comments below and I try to answer them as quickly and correctly as possible. And as always, all that's left to say now is thanks for watching and see you at the next time. Bye bye.